Welcome back everyone to our thrilling episode in the functional analysis lecture series. Today we are diving into the world of weak topology, right? A concept that might sound intimidating at first, but I promise you it is worth every moment of our attention. So to set the stage for this exploration, let's take first a mental journey to a bustling city like Douala. I mean, Douala is actually a very big city in Cameroon. So, I mean, in the daytime, I mean, everything seems straightforward, just like the song topology in mathematics. So the streets are well defined and you can easily navigate your way around. I mean, much like we would hope for in an ideal world. But let's face it, actually, um, I mean, reality is not that simple, right? So even in Douala. So now picture the same city, Douala, at night, right? Softly bathed by, softly bathed in the gentle glow of street light and the cityscape. Obviously, Douala takes a different, more nuanced character, right? So it's like you are seeing it through a weak topology lens. The boundary blurs, and you might, for instance, notice intricate details that daytime couldn't reveal. Say, um, the hidden time of the city, for instance. So the weak topology, I mean, in a mathematical sense, is actually our way of peering into these subtleties, right? Uncovering hidden patterns and relationships within mathematical spaces. It's about actually finding the nighttime version of mathematical structures where the rules of closeness, openness, and convergence are not as strict as during the day. So let's kickstart our exploration, right? So um, consider the dual space E star of a non-vector space E. So consider the dual space E star of let me just write the shortcut of a non-vector space E, right? So far we have two topologies on the dual space. Oops, it's ugly. So far we have two topologies on the dual space E star, right? Namely, the first one is the song topology, right? The usual song topology. I put it in color, so the usual song topology. Right? So that is, I mean, the topology associated to the norm. And E star, right? So we define it in the very first chapter, I think so. So the operator norm of F is the supremum, the absolute value of f of x over the x in E such that norm of x is less or equal than 1. And then we also have the weak topology, like sigma for the weak topology, sigma E star star, right? This is actually the bidual, right? So the weak topology obtained by performing, the same construction we did, right, when we were talking about the weak topology. So if you didn't watch the video on the weak topology, I strongly invite you to do so. So I will put the link at the, I think, the upper right corner of the screen. So now we are going to define a third topology on E star that we call the weak star topology. So we are now going to, maybe I don't have to write it down, right? So I think that's okay. So, but before actually defining the weak star topology, let me just draw your attention on a point. So note that. We can always consider E as a subset of the bidual, right? And this through the following device. So you can see the bidual as just being the joule of the joule. So through the following device, or by so given X, so this is kind of a short proof that we can always see E as a subset of the bidual. So given X, so let me just use another color. So given X in E, right? Let consider the, let's say X, right, define on E star to R, right, defined by phi x of f equals f of x, right? Then I think it's obvious that phi x is an element of the bidual, right? So phi x corresponds to x in E, and this map and the map Richard x associate phi x, right, is actually injective. It's actually injective since it's actually very easy. If you have phi, since, well, let me forget the if phi of x1 say equal to phi x2, right? This means, they agree point-wise. So this means for every f in the, the joule space, let me write it down here. F of x1, which is nothing else as phi x1 of f, right, which is equal to phi x2 of f, right, is equal to f of x2. Okay, so but now since I use since twice, so I'll try to see. So however, I think it's better. So however, the joule space actually separate points. Separate the point in E. So this means, as a consequence, x1 is equal to x2 hence this map is actually it's an injection, right? Of E into the bijoule. So we can always actually see E as a subset of the bijoule. Okay, so now definition. So the weak star topology, sigma, the weak star topology sigma E star E, right? Is the closest topology. Another color, is the closest topology on E star associated to the collection of map associated to the collection phi x running through E, right? So this is of course in the sense of the closest topology of section 3.1, right? So let me put it in bracket here. So in the sense of section 3.1, I will put the link, right? For I think that was actually the lecture on the closest topology, right? So here with x equals E star and yi equals I for all I, right? Capital I, which is here in this case just the set E. Okay, so this is how we define the weak star topology. This is actually the closest topology on a Joule space associated to the collection of maps phi x. So since this is kind of a remark, so since E is actually a subset of the bijoule, right? I think it is clear that the topology, let me use another color. It's clear that the topology sigma E star E, so the weak star topology, is coarser than the topology sigma E star star. So this is actually I mean, again, by coarser I mean that the weak star topology has fewer open set, respectively closed set, than the topology sigma E star star, which is in turn, of course, has fewer open set than the strong topology. Okay, so I think you might wonder, you might probably wonder why in the world someone would be that obsessed in weakening topologies. But the basic answer is that the fewer open set the topology has, the easier it is to extract finite subcover from open covers. so we are hoping to get kind of more compact set. So if you have a topology that has fewer open set, then it has more compact set. And compactness is actually very, 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 very important or fundamental, right? Because it is actually very useful when you want to show that say certain things exist, like minimum or maximum of continuous functionals, right? And it is actually very highly used in partial differential equation, right? Because solution of PDEs are often minimizers of functionals, right? So and then to show the existence, you actually need to at times use the direct method of calculus of variation that heavily relies on compactness. Okay, so let's have some properties of the weak star topology. So proposition 3.11. So the weak star topology is actually Hausdorff. So the weak star topology is Hausdorff, right? So let's have a look at the proof. So again, the idea is actually the same, right? If you have two distant elements, you can always find two disjoint neighborhoods of those elements. So given F1, F2 linear bounded operators, right? With F1 obviously different from F2, right? Then there exists some X in E, right? Such that F1 of X is actually different from F2 of X. So again, just as a reminder, right? So there is no, here we didn't use any Hand-Banach theorem or whatever, right? This is just the definition, right? If you have two functions that do not agree point-wise, that means there is an element X in E such that both of them, such that they did not coincide at that point. So without loss of generality, right? We can assume that so without loss of generality, so we can assume put it here. So we can assume that f1 of x is actually strictly less than f2 of x, right? And of course, because Q is dense in R, right? So you can always find irrational numbers, irrational number between two real numbers. So I'll choose alpha such that maybe just to be consistent, slightly less than alpha, slightly less than f2 of x. Now put say O1, right? It's going to be the set of bounded linear operators such that f of x is slightly less than alpha, right? So observe that this is again equals to phi x minus 1 of the interval minus infinity alpha. And again, go to a set of linear bounded functionals such that f of x is strictly greater than alpha. So consider these two sets, right? So then O1 and O2 are open sets, right? In the weak star topology. So let me just write weak star open. A weak star open set, right? Such that F1 is obviously in O1, right? And F2 is obviously in O2. And O1 and O2 are actually disjoint. So good. So we are done. We found two disjoint neighborhood of our element F1 and F2 that were assumed to be distinct by assumption. Okay, good. So now let's try to kind of construct of basis of neighborhoods of an element F0 in the dual space. So proposition 3.12. So let F0, right, be an element of the dual space, right? So given a finite set, finite collection, right, of point x1 up to xk, right, in E, right, and epsilon positive. Let me just highlight finite. It's actually very important. Now consider the set say V defined, which is obviously, function of x1, x2 up to xk and epsilon, right? So this is defined to be those are linear bounded functionals, right? Such that the absolute value of f of xi minus f0 of xi is strictly less than epsilon. So I just write it in with the Joule pairing notation for every I moving from 1 up to k. So you consider this set, right? Then V is a, I'm going to put it in color. V is a neighborhood. V is a neighborhood of F0, right, for the weak star topology. I feel like it's a bit for the topology sigma. is star A, right? So, and again, as we did for the weak topology, right, we can even obtain a basis of neighborhoods by actually varying epsilon k and the xi and the family xi. So then, moreover, we obtain a basis of neighborhood of F0. Let me highlight basis of neighborhood of F0, right? For the weak star topology sigma E star E, right, by varying epsilon k and the finite family xi in A. Good. So proof. The proof is typically the same as we did, right, for the when we wanted to show that when we define basis of neighborhood for the weak topology, right? So it's basically the same. So I will not write it down. So just write proof is the literal transcription of the proof. I think it was proposition 3.4. I put the link again for your reference. 3.4. So just check the video. So okay, let's have some notation, right? So notation. So if a sequence fn of converges, if a sequence fn, right, of bounded linear operators converges to F, in the weak star topology, we shall write, we shall write, we put it in color, Fn, we put a star here, converges to F. The notation is, typically the same as for weak convergence, right? So you just need to add a star to emphasize that, you're talking about weak star convergence. Okay, so let's have proposition, right? That defines, that gives us some properties about convergence and relationship between weak topology and weak convergence and weak star convergence, as well as strong convergence as well. So proposition 3.13. Okay, so let let Fn be a sequence of linear bounded operators, right? Then first property is that if Fn converges, weak starly to F, then let me just write it. So the weak star convergence is actually equivalent to pointwise convergence. So put it in color. So Fn converges weak starly to F, right? If and only if, I think I'll put it down. If and only if Fn of x converges to f of x for every x in E. Second property, if the sequence Fn converges strongly to F, right? Strongly. Then Fn converges weakly to F, right? In the topology sigma E star E star star. I think we saw that already, right? That strong convergence actually implies weak convergence. So this is basically the same here, and it also implies weak star convergence. So if Fn converges weakly to F, right, in the topology in sigma E star star, right, then Fn converges weak starly to F, law of convergence in the weak star topology. Okay, so this second property is actually also kind of obvious, right? Because we saw that the weak star topology was actually coarser than the weak topology sigma E star star. So the third property, if you have weak star convergence, then the sequence is norm-bounded, right? And the norm of F is less or equal than the lim inf. Typically the same thing as what we did for the weak topology. So if Fn converges weak starly to F, right? Let me write it again, although it might sound like a tautology, but that's okay. Then the sequence of norm of Fn, right? Then this is bounded. And the norm of F, the operator norm, of course, right? Is less or equal than the lim inf. The norm of Fn. And finally, the last property, number 4. If Fn converges weak starly to F, right? And if the sequence, you have a sequence xn of element of E that converges strongly to X. Then the sequence Fn of xn converges strongly to f of x. Okay, good. The proof, as I mentioned already, this is, those properties are exactly similar to what we did for the weak topology. So I just invite you to copy the proof. Of proposition 3.5. Okay. So it is actually very important to observe that if E is actually finite dimensional, then the three topologies actually coincide. So, the strong topology is the same as the weak topology, which is actually the same as the weak star topology. So let's write it down. So remark. So when E is, put it in color, is finite dimensional, the three topologies maybe I precise it again, strong, weak star, coincide. Let's have the proof, official proof. Indeed, the canonical injection, the canonical embedding, J defined from E by Joule, when it's surjective, right? Since the dimension of E is nothing else as the dimension of the bijoule, right? And therefore the weak star topology coincides with the weak topology. Sigma E star E is equal to sigma E star star. Okay, good. So now let's have another proposition, which is actually very important. So proposition 3.14. Okay, so let phi be defined from the dual space into R, right? Be a linear functional that is continuous for the weak star topology. Let me just drag it. That is continuous for the weak star topology. Then, let me just highlight the most important. So it should be a linear functional. Then we need continuity for the weak star topology. Then there exists, put it in column, there exists x0 in E such that phi of f is equal to f of x0 for every f in the dual space. Okay, good. So the proof of this proposition actually rely on a lemma. So we just kind of prove the lemma before proving the proposition. So the proof relies on the following useful algebraic lemma. And this would be lemma 3.2. So let X be a vector space. So there is no topology involved. And let phi 1, phi 2, up to phi k, right, be k plus 1 linear functionals on X. Such that the following implication hold. So let's call it 2. Such that put it in column. Probably this one. Such that phi I of v equals 0 for every I moving from 1 to up to k, such that this implies that phi of v is equal to 0, right? So this is of course for every v in X, right? So if this implication hold, then there exists constant say lambda 1, lambda 2, lambda k in R, such that phi is actually a linear combination of the phi I. Okay, so let's have the proof of this lemma, right? So before we state the proof, before we start the proof, let me just recall something. I mean, this, I mean, you can actually view, I mean, the property 2 as say, how can I hide it again? I think that's okay. Well, let me see. Well, people, I think it's often can actually view it as V belong to the intersection of the kernel of the phi I moving from 1 to k. Then this implies that V is actually, I mean, maybe not. I think I can just even say that that the intersection of the k of these things is actually contained into the k of phi. So you can also kind of restate the theorem in this way, but that's okay. Okay, so let's move to the proof, right? So proof. So consider the map. Consider the map F, right, defined from X into R k plus 1, right, defined by say phi of u equals this vector, put it like this, defined by f of u equals phi of u, and then up to phi k of u. So from assumption 2, right, it follows that from assumption 2, so it follows that the vector A is equal to 1, 0, 0, 0, because 0 k times, follows that A, right? I think that was a bit too big. Let me just write it fully. So it follows that A does not belong to the image of F, right? Since I put it in bracket, since if phi I of u equal to 0 for every I, right, moving from 1 up to k, then we should necessarily have phi of u equals 0 as well. So A is not an element of the image of F. So thus one can actually strictly separate, thus one can strictly separate A and the image of f, right, by some hyperplane in the space Rk plus 1. So this means that one can find lambda, constant lambda, lambda 1 up to lambda k, right, and alpha also in R, such that just for matter of clarity, so such that now this is the scalar product, so let me write it this way: lambda lambda 1 lambda k of A is strictly less than alpha, strictly less than the scalar product of lambda lambda 1 to lambda k, right? Scalar product with phi of u, phi 1 of u, phi k of u. And this should hold for every u in X. So this means, I mean, if you compute the scalar product, so this means lambda is actually strictly less than alpha, which is strictly less than phi of u, right, plus lambda phi of u, plus the summation over I moving from 1 to k of lambda I phi I of u. So this inequality holds for every u in X. So again, from these inequalities, it follows that so it follows, I mean, if you take u to be the 0 vector, right, so you get that lambda is actually strictly less than 0, so it follows for just write, it follows that, let me just write it. So it follows that lambda is strictly less than 0, just put it in bracket and consider u equal to 0 of x, right? So to see that lambda is strictly less than 0, and that because X is actually a vector space, that lambda phi of u, right, plus the summation over I moving from 1 to k of lambda I phi I of u is equal to 0, right? I mean, this whole because, I mean, X is actually a vector space, but maybe it is not, I mean, it's not clear, so let me try to make it clear for you. So because X is a vector space, so the above inequality also holds for, say, beta u. So you will get something like how would I write that? So you get something like, I mean, if you replace u by beta u by minus beta u, I would say, yeah, by minus beta u, yes, you will get something like, I mean, or consider, say, minus beta u, right, for every beta in R. We get, I mean, if you replace everything properly, right, we get the absolute value of, we put absolute value of beta outside, right? It's a matter of clarity. So you get this lambda phi of u plus the summation where I moving from 1 to k of lambda I phi of u phi I of u. We get that this is actually strictly less than minus lambda, right? So but this should hold for, for every beta in R. But actually, you can actually make beta arbitrarily very, very large, right? In such a way that this inequality doesn't hold anymore. So for that, by making so necessarily, I think I should just write it like that. So necessarily lambda f of u plus the summation of lambda I phi I of u should be 0. I moving from 1 to k. So this is, this would be the argument actually. Okay. So I think we are basically done, right? So because this is for everywhere, so this equals to 0, and lambda is actually different from 0. It was strictly less than 0, so you can pull the summation on the other part of the equality, and then you get that phi of u is equal to the summation over I moving from 1 to k of minus lambda I over lambda, right, of phi I of u. And this holds for every u in x, and we are done. Okay, good. Now let's go back to the proof of our proposition. So proof of proposition 3. I think it was 14, I think so. So okay, good. So in proposition 3.14 we had phi a linear functional, right, which is actually continuous for the weak star topology. So since phi is continuous, for the weak star topology. I don't know why I always think of putting hyphen between weak star and topology. So since phi is continuous for the weak star topology, it is continuous. Because it is continuous everywhere, right? On the whole domain, it's continuous, particularly at 0, right? 0 of the dual space. So this means, if I want to write things, so this means for every epsilon positive, right, there exists a neighborhood, say V, right, of the origin, right, such that the absolute value of phi of f minus phi of the 0 of the origin, right, is strictly less than epsilon whenever f is actually in that neighborhood. Well, but this is actually 0, so this is 0, and then because epsilon is arbitrary, I can take epsilon to be 1, for instance. So this means absolute value of phi of f, say, is strictly less than 1 for every f, whenever f is actually in the neighborhood V. So okay, so I think I don't remember the proposition number, but we saw how to characterize neighborhood of a point, right? The weak star topology. So we may always assume you may always assume that V has the following form. Those are the set of linear bounded operators, right? Such that the absolute value of f xi is strictly less than epsilon, right? For every I moving from 1 up to k, right? For some xi in E and epsilon positive. So in particular, if you have, if the absolute value of f of xi, right, is equal to 0 for every I moving from 1 to up to k, right, then you agree with me that for every lambda in R, lambda f xi is equal to 0, right, which is obviously strictly less than epsilon, right, for every I moving from 1 up to k. So this means that for every lambda in R, lambda f is actually in the neighborhood. It's actually in V, actually. So this means, and then we know that whenever I have element in V, the absolute value of, so this means for every lambda in R, the absolute value of lambda times phi of f is actually strictly less than 1, right? And again, for the same reason as we did in the 3.2, right? So this necessarily implies that, so necessarily, because you can make lambda arbitrarily large in such a way that, this doesn't hold anymore. So necessarily f should be in the k of phi. So that means phi of f should be equal to 0, right? So now we can use the previous lemma. So according to the lemma 3.2, so let me highlight that. Lemma 3.2, phi of f is nothing less than, it's a linear combination of phi of f of xi, I moving from 1 to k. And this should hold for every f in the dual space. Well, how is lemma 3.2 being applied here? Just consider the sequence. Not really the sequence, but yeah, the finite sequence of maps phi I defined from the dual space into R, right? Which at f associate phi I of f equals f of xi, right? So we saw that if phi I of f is equal to 0, right, for every I moving from 1 up to k, then this implies that phi of f is equal to 0. So this and this is exactly the assumption of lemma 3.2. So that means assumption of lemma 3.2 essouffled. Good. So we are done. Okay. So as a consequence of the above proposition, so we have the following. So corollary 3.15. So assume assume that you have a hyperplane in the dual space. So assume that H is a hyperplane in the dual space, right? That is closed for the Weak topology. So that is closed in the topology sigma E star E. Then we can further characterize this hyperplane as being of the form then H has the form so H is nothing else than the set of linear bounded operators such that f of x0 is equal to alpha, of course, for some x0 in E, right? Such that x0 is different from 0 and some alpha in R. Okay, good. So let's have a look at the proof. Okay, so since H is a hyperplane, since H is a hyperplane in the dual space, right? By definition, so by definition, there exists a linear functional. There exists phi. I don't know how to write it. There exists. Let me write it rightfully. So there exists a linear functional phi, right? That do not vanish identically, right? Linear functional, say on A star phi, right? That does not vanish identically. So this means, right? And there is this also constant alpha in R such that H has the following form. Those are the F in E star such that phi of F is equal to alpha. Okay, now what we want to show is that, let me write it in probably in color. So we want to show, we want to find, so we want to find say x0 in E, right? X0 different from 0, right? Such that for every f in the dual space, phi of f is equal to f of x0. I mean, if you can find such a point, then we are done. So this is the main idea of the proof, actually. Okay, good. Now, so we need somehow to make use of proposition 3.14. So according to, because this is a corollary, so according to proposition 3.14, right, it is enough to show that phi is weak star continuous. Weak star continuous. Okay, good. Because remember proposition 3.14, I mean, if I have a linear functional on the dual space, right, that is actually continuous for the weak star topology, then there is this an x0 in E such that phi of f is equal to f of x0. Okay, so let f0, right, be an element of H complement. So this means f0 is not in H, right? Since H complement is actually is weak star open, right? There exists a neighborhood, say V, right, of f0, I mean, in the weak star topology, of course, sigma E star E, such that V is contained into H complement. And again, we may always assume that V has the following form. We may always assume that V has the following form. Those are the linear bounded functionals such that absolute value of f minus f0 xi, this is the dual pairing for every I moving from 1 up to k, right? For some xi, of course, and epsilon positive. Okay, so, and then we also have, phi of f0 different from alpha, right? Since f0 is not in H. So either phi of f0 is actually strictly less than alpha, right? Or phi of f0 is actually strictly greater than alpha. So assume without loss of generality, that phi of f0 is actually say strictly less than alpha. So now you want to show that under this assumption, this implies that phi of f is actually strictly less than alpha for every f in the neighborhood of f0. So we aim at showing now, I'm showing that phi of f strictly less than alpha for every f in the neighborhood of f0. Okay, so by contradiction, right? Assume that, so by contradiction, assume that that there exists an f in V such that phi of f is actually strictly greater than alpha, right? Then the following map that I call say theta, which at t associate phi of, convex combination of f and f0, say tf plus 1 minus t. Then this map is actually continuous. It's continuous on 0, 1, right? Such that say we write theta of 0 equals phi of what? Phi of f0, right? Which is strictly less than alpha by assumption, and theta of 1, which is nothing else than phi of f, which is strictly greater than alpha by assumption. So by the intermediate value theorem, there exists, say, f tilde, right, in f0f, right? There exists a linear bounded operator, right, which belongs to H. So the can find a linear bounded operator such that f tilde of such that phi of f tilde is equal to alpha, right? But this segment is contained in V, right? And V is actually convex. And V is actually convex, right? You can easily prove that. So this means that V intersect H. So V intersected with H is non-empty. But this is absolute, right? V was actually a subset of H complement. So therefore, phi of f is actually strictly less than alpha for every f in the neighborhood of f0. So therefore we obtain phi of d strictly less than alpha minus phi of f0, right, for every g in W, which is defined to be as v minus f0. I mean, this is just by definition of the set V. I mean, this is basically, I mean, it is actually easy to see actually. There's nothing to prove here. Okay, so, and since minus W is equal to W, right? So we get that the absolute value of phi of g is actually strictly less or equal than, I mean, it's less or equal than absolute value of alpha minus phi of f0, and this for every g in W, right? So however, W is actually v minus f0, and v was actually a neighborhood of f0. So however, W is a neighborhood of the origin, right? So it follows that that phi is continuous at 0 of E star for the weak topology, for the weak star topology, for the topology sigma E star E. So by linearity, it's actually by linearity, phi is weak star continuous on the whole domain. Now applying proposition 3.14, like that. Applying proposition 3.14, we conclude that there exists x0 in E such that phi of f is equal to f of x0 for every f in E star. But well, you want x0 to be different from 0, and which is actually the case here, right? So, so we are done. Typically, I mean, x0 is necessarily different from 0. Otherwise, you will get phi of f equals to f of 0, which is equal to 0 for every f in E star. So this will mean that phi is actually 0, which is, I mean, which contradicts the fact that phi does not vanish identically. So which contradicts the fact that phi does not vanish identically. So we are done with the proof. Yeah, I think so. Yes, we are done. Okay, so I think it's a bit important to comment this. This proposition. So remark. So let's have a remark. So okay, so assume that the canonical injection is not so let me write it. So assume that the canonical injection, the canonical embedding, right, those J defined from E to E star star is not surjective. It's not surjective. Then the weak star topology is strictly coarser than the weak topology. Put it in color, then the topology sigma E star E is strictly coarser than the topology sigma E star star. This is actually the weak topology on the Joule space, right? Because we can actually, for example, this has to do with our last theorem, our last corollary. So, for example, let's say phi, again phi, yeah, is an element of the bijoule, right? And phi is not in the image space of E through the canonical embedding. So then the hyperplane, then the set H, defined to be the set of inner bounded operators such that phi of f is actually equals to 0, right? This is close in the weak topology sigma star, sigma E star, E star star, right? But in view of corollary 3.15, it is not close in the weak star topology sigma E star E, right? Typically because you cannot find an x0 different from 0 for which, you put it in bracket as one cannot find an x0 in E, x0 different from 0, right? Such that phi f is equal to f of x0, where we have E star. So this is the proof that that the when the canonical embedding is not surjective, the weak star topology is actually slightly coarser than the weak topology on the Joule space, because this is actually a typical example of a closed set for the weak topology, right, on the Joule space, which is not closed for the weak star topology. Okay, so I think with this, we are going to, I mean, with this we kind of, I think the next step will be to talk about the Banach-Arrow Bourbaki theorem, right? But I think this will be in the next video, and I think we will stop here for today, right? So we end this lecture series. I mean, this video on this corollary, and then we see again each other in the next video.